A test was given to a group of students. The grades and gender are summarized below. So we have a table here. We have male and female students and their totals for our rows, and then for the columns we have A grade, B grade, C grade, and the totals. So here in this first box, males who got an A, males that got a B, males that got a C, females that got an A, females that got a B, females that got a C, and the totals. If one student is chosen at random from those who took the test, find the probability that the student was female given they got a C. So this is a conditional probability question. We want to know what's the probability that the chosen student is female given a C. So given the C means we're interested in this column here, the C column. Given we know that the student got a C, what's the probability that the student is female? So our favorable outcomes, preferred outcomes would be the females in the C column, and the total would be all students got a C. So females who got a C divided by all students who got C's, who got a C. So that would be female students who got a C divided by all students who got a C, 7 out of 10, or 70% or 0.7, as it says here, 0.7. So basically, when we're finding conditional probabilities like this one, the probability of A given B, it's the outcomes for both A and B divided by the outcomes for B, all B outcomes. So this was the outcomes that were both female and C, so the students that were both female and C students, divided by all the C students. So that's all we're really finding with a basic conditional probability where you have one thing given you already know something else. This idea for conditional probability can also be applied to this example of results for a medical test. So the probability of A given B was outcomes for both A and B and all B outcomes. So we're going to just be using this over and over when we find sensitivity, specificity, the PPV and the NPV for this disease. So yes, here we have a new medical test given to a population where the disease status is known and the results appear in this table. So the rows are the test results for positive or negative, and the columns are those that have the disease and those that do not have the disease. So in this first box, 177 of those tested were tested positive and had the disease. This 162 tested positive but did not have the disease. Here in this box, 52 tested negative and had the disease. And in this box, 172 tested negative but did not have the disease. So we want to find the sensitivity of the test. The sensitivity of the test is basically the probability that there's a positive test result given has disease. So it's just a conditional probability. So that is equal to those that test positive and have the disease, so that's 177, divided by all that have the disease, so that would be 177 plus 52. So this would simplify to 77.3%. So that's sensitivity. It's just positive test result given has the disease. Specificity is the probability of a negative test result given does not have the disease. So that's this column here. And it's outcomes for testing negative and do not have the disease. That's this box here. 172, both tested negative and did not have the disease. And then the bottom would be all that do not have the disease, 62 plus 172. And then you simplify this to get 73.5% specificity. The probability of a negative test result given does not have the disease. What's the probability that someone who tests positive actually has the disease? So what's the probability that they have the disease given they test positive? This time. Someone testing positive, someone having the disease given they test positive. So this would be this first row for positive because it's the positive test result that's the given. And then we want to know how many out of those have the disease. What's that likelihood based on the results that are in this table? So that is the results that are positive test results and have the disease. So that's 177 divided by all that have positive test results, 177 plus 62. So this is the probability of having the disease given a positive test result, and this is the same thing as the positive predictive value. That's what positive predictive value is. This will simplify to 74.1%. The probability that someone who tests negative does not have the disease is probably does not have the disease given negative test result. This is the negative predictive value. Probably does not have disease given negative result. So the outcomes that are negative and not having the disease. So that's this row here where negative results are given and we're interested in those that do not have the disease. So there's 172 that are both the negative test result and do not have the disease. So this is 172. And then the total for all the negative test results would be 52 plus 172. So that's 52 plus 172. So this represents the probability that someone does not have the disease given a negative test result. That's the negative predictive value. Simplifying will give you 76.8%. So all of these ideas, positive predictive value, negative predictive value, specificity, and sensitivity are really just this conditional probability formula being used again and again.